Right. So, like everything else, we start off understanding the basics and then go from there. All right. So generally, we write the function as f of x comma y. F of x comma y takes the place of z. All right. So you might have something that says z equals x squared plus y squared, for example. It could also be written as f of x comma y equals x squared plus y squared. Right. Just like f of x, it can be thought of as y. F of x comma y can be thought of as the z. All right. X and y are independent variables and are chosen independently of each other. All right. So they're unique independent variables. All right. They could coincide with one another, but that's not what you're expecting going in. All right. That I already addressed. The graph will be a surface embedded in some 3 space. All right. So that's the thing that kind of makes this different from everything else. And that is the idea that if you define your variables in a 3-dimensional plane or 3-dimensional realm, I guess you could say, then characteristics of 3 space will come into play. Right? So now if you have 3 variables, and it makes it even more obvious, but we've talked about cases where there's an implied 3rd variable, where if I were to say something like y equals x, you would think that that's a line, but it's implied that it's for all values of z. So it's creating a plane. All right, so a line with infinite height, if you will. Not every surface is a function because by definition, f of x comma y will generate exactly one output for z given x and y. All right, there's an equivalent of the vertical line test from 2 dimensions, which is that of a surface in 3 dimensions is a function if and only if no line parallel to the z-axis intersects the function more than once. All right, so that's how we define something as a function, but really at this point we're not kind of quibbling over that sort of designation. It's really more so we're going to kind of get a sense of structure and how calculus works in this sort of context. All right, we'll worry about things like whether it's a function or not later on. All right. And in a lot of cases, it's pretty obvious when something is a function and when it isn't. But we'll formally discuss that down the line. The domain works the way it always did. So you have 2 variables to account for. So you have 2 ways, really, in which you can restrict your domain. You could restrict it for x, you could restrict it for y. Right? So your domain is not only all possible values of x, it's possible values of y as well. Your range would correspond to possible values of z. All right, so x and y are your 2 independent variables. There are domains associated with those variables that need to be accounted for. All right, so with that in mind, we take a look at a function, f of x comma y, and we say, well, what's the domain of it? Well, you look at it and say, what's the problem? Well, there is no problem with y. Y could be anything, right? So y belongs to the set of all real numbers. All right, there is no restriction on y. It could be anything. It's x that would be the problem, right? So x, well, you can't take the log of a negative number, and you can't take the log of 0. So negative x has to be greater than 0, which implies that x has to be less than 0 itself. All right, so these are just little notes that I'm writing because we do need to formally compile all this into one specific domain. All right, so how do we write the domain in 3 space? We say the domain is x and y such that x less than 0 and y belongs to the set of all real numbers. All right, interval notation or set builder notation are fine, but generally, you can make the choice on your own. We use the and symbol here because they wouldn't have to occur at exactly the same time in that, like if x is equal to, for example, -1, that wouldn't have to be at the same time that y is equal to a 7, for example. But these two have to happen concurrently in order for this function to exist. All right. If it's one or the other, that could be a problem. Maybe, maybe not so much here, but over here. You know, if it's an or situation, logically, you know, just going back to, I mean, actually going back to, I don't even know if you learn logic. If you did some computer science, then you definitely learn logic. And in order for a statement to be true, both parts have to be true. For an or statement to be true, either part needs to be true. So an or would not make sense here, because if this were false and that was true, it would return a true result, which would not work.
I'm kind of used to the and symbol being like a multiplication problem.
Oh, well, okay, so you're going to want to not do that. Because I'm used to that being multiplication, and that could be a problem.
What is the symbol to the right of the Y? That T?
Oh, this bad boy here? Oh, that bad boy.
Yeah.
It's like a funky E.
No. The bottom one.
This one?
Yeah, is that?
Yeah, it's like a funky E.
Same thing.
It's supposed to be the same as that.
Is all real numbers?
That's the all real
No,
numbers.
but that's-
Belongs.
Okay.
Yeah.
Is a funky ampersand acceptable in place of a triangle or a caret?
Wait, what's the
Because I don't. Where does that come from? I've never seen that.
You've never seen a logical connective and?
I've seen
Nah, I
a
haven't
logical
either.
connected and, but not with that caret.
I will allow the intersection and the union notation.
What the?
So the U, or in this case the upside down U.
So that's a U?
No, this is a V, upside down V. It's a logical connective that means or.
We use
Wait, that should mean a word.
You know what I'm talking about? What kind of looks like a?
Yeah, it's like,
It's
Can we
like
just
a
define
straight
that?
line or a loop, and then.
yeah, it's like freehand,
No,
like.
it's a serious and symbol. It's from. It kind of looks like a music thing.
Yeah, like
Yeah.
the ampersand. Yeah. Oh no, like don't get me wrong. I'm a pro at that bad boy. Check this out.
Oh, look at that.
I mean, it's like I typed it.
I mean, mine won't look like that, but.
I mean, it's gorgeous. Unfortunately, that's not an appropriate notation. So.
Why are we using an or symbol? You just.
Oh, that's what the issue is. Okay, yeah.
Is it an or symbol?
I realized what the issue is. I keep saying or, but it is and.
That's it.
This is an and.
Yeah, I've seen that.
Yeah.
Why do we need the second and term if it's always true? That's like saying while x is less than 2 and true is true.
Pretty much why logic doesn't make any logic.
Like it's. You
Well,
just-
there's no common sense to logic.
No, not
Yeah.
at all. Yeah.
You know, like if I said that Charlie is wearing a green shirt or jeans today, and Charlie walked in with a green shirt and wearing jeans at the same time, you would say I was wrong.
No.
Because mathematically it's correct, but it just vernacular, like common
Logically,
conversation, it just doesn't sound right.
That was an awful class.
Yeah.
Hate logic.
Digital logic.
Did,
Hate logic.
do they do that in discrete here? Anybody take discrete?
No, not here.
They do that logic, you know, like modus tollens and modus ponens. Oh, that's great,
I used
good
to
stuff.
have arguments with my professor like this does not make sense.
So you must really have loved the false implies true is true.
I hated it.
Oh yeah, that's a good one.
That's a good little.
Any sentence based on a false premise is true.
Yep.
So
Yep.
I'm just asking why we need the secondary term. It's not really defining our domain in any. It's not limiting our domain in any way.
it doesn't have to, but it's stating our domain. Just like if I said, "What's the domain of y equals x squared?" and you did not tell me negative infinity to infinity, like you didn't answer the question, you know. Now, if I were to say, "Are there any restrictions to our domain?" Now you have a point. But here it's saying, "Find the domain." You got to tell me, you know. So therein lies the problem. So for number 2, well, number 2 and number 3, it's like, you know, the classic funny business when it comes to functions, even in 2 dimensions, is that you're looking at cases where it could be undefined or imaginary, right? So in the case of number 2, there's a couple of instances where it could be undefined, a bunch actually. So, but it all comes back to the idea that x squared minus y squared would need to be equal to 0 in order for that to happen. All right? So you look at this and say, all right, now what? Well, you can go one of two ways. My preferred approach would be to factor, which is, of course, nobody's favorite approach except for mine.
You can move it to one
You can move it to one side,
side though.
but then you get into the plus or minus conundrum. And I only go this way because I even on this level, half the class forgets the plus or minus. You know, the other class does very well, but yeah, it becomes an issue, right? So this way you're I don't want to say you're guaranteed, but you're more likely to include both the positive and negative outcome, all right? So then you set each of those factors equal to 0 because you learned about quadratics like in every course you've ever taken for some reason. I feel like it's all just for this moment. But I do like the way life works out is that I teach this in my Algebra 1 class on the same day I'm going over this in Calc 3. And I tell them in Algebra 1, listen, you're going to need this every year that you take math from here on out. And then right now I can actually say, yep, I wasn't lying. I'm just like, you needed to solve a quadratic. It happens. Or at least use quadratic techniques. So x equals y, x equals negative y. You could look at that one of two ways. You could say x equals plus or minus y. Or you might say y equals plus or minus x. Since they're both equivalent, it doesn't matter which one you write because in the end, we still need to make a final statement on our domain. And that keeps happening. Ay, 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 ay. And again. No idea how close it came to me just being like, forget it, class is over. So the domain is x and y such that, well, they're both saying the same thing, right? So now you just got to be careful because these are not the values I want, right? Because they're supposed to make it equal to 0. So I would say x cannot be equal to plus or minus y. You could absolute value it. Any way that gets the idea across is fine, as long as you're using appropriate notation. All right. So I'm exercising my teacherly right of doing the easy ones in class and leaving the difficult ones for you to do. They're not difficult. They're not. They're basically talking about the same idea. 4 is actually easier than all of the other ones. But number 3, you have to account for the radical, in addition to the fact that that expression is in the bottom of the fraction. So there's that part of it, but nothing too crazy. Your domain than others. In the case of number 3, you're going to do a little bit of work, but nothing too crazy, because you kind of get boxed into a corner or painted into a corner pretty quickly, because 9 minus x squared minus y squared, it's a radical, so it's got to be positive, but it's also a denominator of a fraction, so it's got to be more than 0. It can't be equal to 0. So it's got to be more than 0 in order to be positive and unequal to 0. All right? Really, the only thing that you can do for something like this would be to move the 9 over and negate both sides. So I have negative x squared minus y squared greater than negative 9, but when I negate both sides, I'm going to get x squared plus y squared is less than 9. I'm going to switch the direction of the sign. So that's all side work to help me come up with my domain, which is actually pretty simple, because all you need to do is establish under what circumstances your function will not exist. All right, I have a function that's defined in terms of x and y. All right, that will only exist if these conditions are met, and that is x squared plus y squared must be less than 9. All right.
X plus y is less than 3.
Unfortunately, no, because the square root of x squared plus y squared isn't x plus 3. Because if that were the case, then x plus 3 times x plus 3 would distribute out to equal that. But it ends up being x squared plus 6x plus 9. So that's something to be avoided. And in general, once you come up with a relationship between the two variables, unless it could be put simply like something like this, just leave it. Yeah, Kev.
So you factored out the -1, or you just kind of like switch?
I did a switcheroo. What I did was I divided every term by -1,
Yeah.
which is essentially the same thing as factoring out the -1 and then dividing. So, but when I divided each term by -1, it also impacted the direction of the sign.
Right.
So you just got to remember that for inequalities.
Why?
Mm.
Number 2, at least when we were doing it last semester, I just did the notes. And I'm like, you were like, make sure you write down that x and y are in the sum of the field of all real numbers in the domain. But I see.
Oh, and number 1. I was looking at number 2. I know you were talking about number 1, but I was looking at the wrong thing. Yeah, because y could be anything, depending.
I thought you made a fuss last class about making sure that you also put down that x and y are in the all real numbers like section. They just can't be equal to each other.
Well, I made the fuss about that bad boy. That's what I was fussing about.
And?
We all remember the fuss, right?
And.
Yeah, the and symbol. I mean, I was calling it or for like a good 2.5 minutes, but that was where my fuss was. It was the idea that we had to establish what x and y had to be, but in this case, you had to be looking at values for x that were less than 0, while also having y values that belong to a set of all real numbers. All right, so that's the distinction there, because you need both of those conditions to happen simultaneously. In the case of number 2, for example, it turns out that these are the only situations that would allow it to be undefined. So we're just stating what it can't be equal to. And this is a case of or, really, because it's saying x is unequal to y, or x is unequal to -y. So it's an implied or in the not equal symbol. But in this case, it's an actual entire region of real space for which a graph doesn't exist, right? Because you got to remember, we're talking about functions of functions in terms of 2 variables. So this is a circular region with an outer boundary that is 3 units away from the center of the region, right? Because the radius is equal to 3. So that entire region is the only region in which we would be focusing our energy. Anything else would fail to exist, right? So this is really excluding everything else. But in this case, it really had to be stated because you had 2 independent variables in your function that were products of one another, and so they each kind of played a different role in the function itself. Right? In the cases of 2 and 3, they're combining together, so it's a little bit of a different story. Right. Now, number 4, that's an easy one to look at because cosine functions are everywhere continuous, assuming x and z are real numbers. So here I could just jump right to it. My domain, x and y, such that, oh, it's f, geez, I missed it. We are not ignoring z. The last 3 had no z's in them, even though I said z. Oh, hold on. All right, so we don't have to worry about z because that's not going to make anything undefined. All right, so such that, what's the story here? X can't be equal to 0, but not at the same time, right? If either one of them is 0, we got a problem. Yeah? So, or y can't be equal to 0.
So that logic comes in.
Yeah. And now we don't have to worry about z in terms of the function existing, and z belongs to the set of real numbers. That was an exclamation point. All right, so in terms of defining continuity, I'm not worried about what z is going to be because it could be anything, but x and y have the restrictions.
Do you, are current, like, I guess parenthetical and or is okay, like, I want to say this or whatever the result of this is, like another or statement.
Like a conditional?
Like if I had,
Like if this is true, then that?
like I have a or, but one of the terms is another or. One of those terms is a thing.
Oh, so either this or that or that?
Yeah, so like if that or statement is false, but like one part, like I don't know how to describe it.
Well, the minute you say if, I'm thinking conditional.
Yeah, it is a conditional. So like if I had to, like, could I do something theoretically where, like, let's say we had a function where y could not be equal to 0 at the same time as z being some defined term, and like just that, and I said x is not equal to 0, or if that is true, then like
Yeah. In parentheses, you'd have to use a conditional though. So nice sideways arrow for you. I don't plan on putting anything on the test that requires you to do that. The one that means if then. So it would be something like, I'll just throw you an example. I mean, I don't have a function that is the example, but something notation-wise, kind of along those lines. It would be something like you have x is not equal to 0, or y is not equal to 0, then z has to be greater than 0. I don't know, whatever.
sometimes z could still just be independent, like, and you just throw another and or there, like they're not.
Well, if it's independent, then it doesn't matter what the connector is, because
So,
generally. But that's what a conditional would look like, because it would assume that if this is true, then that would be the result. All right, but that, I mean, I don't want to do that. So, yeah. No. Yeah, no. There is a place for that. There's definitely a place. Oh, hello. Ah, all right. Cool.
A little late.
A little bit.
No, I just have a question. Is there like an and? Is there a state where you say and or? Like, is there a symbol for that?
Not to my knowledge.
Because I'm saying.
Diamond, exactly. Not that I know of. If there is, I'm ignorant to it.
Kind of just wrote the answer.
And or is what it, like.
Yeah, like either both. You know.
Well,
Yeah.
that's an or, just there, the or encompasses and, but that was a little
And then just.
Oh, that would be the case of the green shirt and the blue jeans.
Yeah.
Yeah, that would be an and or, which is still encompassed under or, as you said. Very good. Graphing equations in 3 space. Very exciting. So you've been able to kind of see how this stuff, see how it looks on GeoGebra, but you've been desperately waiting for your opportunity to be able to do this all out by hand. And so, you know, we tackled a couple of instances, but we didn't really go too crazy with it. All right, some cases are easier than others. In the case of, oh, I decided not to number these for some reason. All right, well, this is number 1, this is number 2, and so that's 1 typo bonus opportunity, number 1. Number 2, that would be another typo bonus opportunity. Is there a number 3? Oh, 3 typo bonus opportunities just on page 52. All right. So, the fact that there's no numbers, yeah. Very generous. So we have a relation here, x minus 4 times z minus 2 is equal to 0. So, I mean, in factor form, you have the zero product property. It would be true if x minus 4 is equal to 0, or z minus 2 is equal to 0.
Or, isn't it? Never mind.
This time it really is or.
It's upside down.
Yeah.
Wait, so,
The one that's almost an A is and.
okay.
So the or is upside down. Hey.
Yep.
V or upside down V.
So it's a V.
Yes. So it's a V. V is or.
Upside down.
P.
So I always just, it was enough for me that the and would almost look like an A. That was like, okay, so that's my A. The other one is the or. And that was good enough. At least until tonight, apparently. So we have two possibilities. X is equal to 4, or z is equal to 2. So this actually doubles as our domain, because these are the values that satisfy this equation. So, you know, we're limited in what we can work with here, because what this is telling us is that x equals 4 will satisfy this equation, but x equals 4 is not just, you know, a point on a graph. You know, we're in 3 space now. This is a plane. Where x is equal to 4 for all y and z. Z equals 2 is a plane. I'm going to go blue on that one for those keeping score at home. Where the z value is equal to 2 for all x and z.
For all x and y.
For all x and y, thank you.
Let's see.
Well, yeah.
No.
Thank you. So, I'm going to graph x equals 4 somehow for all the values of x and z. So what I have to do is create a plane here and make it look kind of planey.
So I'm just curious, why do you use the and symbol there but not at the top?
Because it's not part of the domain notation. Look at those quality ampersands right there. You just pop right off the page at you.
How do you feel about the ones that are just like the line?
Oh, those Fugazi ampersands where like no real effort are put in.
I just make a plus.
Yeah, I mean it just demonstrates the the lack of willingness to go the extra mile. Yeah, it's kind of like, I don't know, if I were interviewing somebody for a job and they gave me that little Fugazi and symbol, and then the next candidate came in and gave me a gorgeous ampersand like I would do.
What situation would call for that?
I mean, totally. I mean, you'd have a job like right away. I had to do a writing sample in order to get my job at the high school. There were ampersands all over that bad boy. I'm pretty sure that's the only reason I got the job, because my demonstration lesson bombed royally. No, actually it was fine. It's just it was in the middle of the summer and there were no students, so I had to teach to a room of administrators. And
My teacher really screwed up before my high school. It was ugly.
oh, I've been in the room when people have crashed and burned before. I'd be like, oof, wait, so you went to school to do this? You may want to consider going back. Yeah, it's not good. Definitely not. Yeah, so anyway, I have to create a plane that's going to go through the x value of 4, but it is also going to somehow account for all possible values of y and z. What I do is I take advantage of the graph itself. And so I know what the plane, the yz plane, looks like according to this graph. all I'm going to do is reproduce that just at the x value of 4. All right, so I'm going to take advantage of parallel lines. So I'm going to draw a parallel line to the y axis over here, poorly of course, and then a parallel line to the z axis, which makes it straight up vertical, up as close to vertical as you can do. Do a little shading, kind of, sort of.
Are you gonna curve and do this?
Yeah, because otherwise I'm going down like to here. So, yeah, you can do that.
He's hand drawn 3D graphs, right?
Eyeballing it, or is it?
Well, what I did is I took this line, reproduced it down here at x equals 4, and I took this line, reproduced it over here to make it parallel to z, and created a rectangle out of it. But I did eyeball it.
So what I want to know is that, does this mean that these statements are always true except for when those two planes intersect? Is that what it's stating?
No, it's also true when they intersect.
Because it says or.
True or true is true. The only time an or sentence is false is when both parts are false. So if you give me something that does not satisfy either of them, then it would be false. But if it satisfies either part of them, then it's automatically true, even if it satisfies both. That's the green shirt and jeans conundrum.
So because the domain of the two, or at least for that function, since it's always going to be all real numbers, this statement is always true. You're just asking us to draw it out.
Just drawing it out, yeah.
Can you show us the graph on GeoGebra?
I can.
Okay. Because this
So
is.
does it stop at z is equal to 2, or?
Well, I haven't done that yet.
Plane.
I just did the red one. Now I'm going to tackle the blue one.
Oh.
So then what would be the case for, let's say, it was x minus 4 times something where the denominator could equal 0?
You would just skip whatever that value would be. That would
So
make the
then
denominator
would be,
equal 0.
It's always true except for that.
Yeah, there might be like a strip of a gap in whatever the plane is. But it could also be the way asymptotes manifest themselves in 3 space is that they're still surfaces, so they'd be like waterfalls kind of. So instead of asymptotes going like linear, like curves going up to the same location, it would be entire surfaces that are bending towards each other, folding in towards each other. So it might be something like that.
Because this is an or statement, even if one of the statements wasn't true, like you said, there was an asymptote or it was a denier where it could be 0, it's still true throughout the entire domain. It's an or.
Correct.
Okay.
All right, so now I'm going to tackle the z equals 2. I need it to go through 2 and also have characteristics of the xy plane. So I have a sense of what the xy plane looks like. So what I'm going to do is I'm going to reproduce this line going through 2. All right? So I'm going to do that in blue, eyeballing it again. Okay, eyeballed it too much. Okay, shaky hand. There we go. All right, so that's roughly parallel to x. That's what I was going for. Y is the horizontal, so that part's easy enough. And then I might have to do some erasing just to make it look roughly equivalent or decent, but like this. Bring this out and over. Erase this extra bit of, oh, it won't let me erase it. That's funny. Get the white out. Get rid of that because I don't need it. And again, maybe something like that. And then just blur your vision like a lot. And then you can kind of see.
So it's supposed to be that the xy plane is moved up to 4 on x. I mean the zy plane is moved up 4 on x.
The the ZY plane is moved out to 4 on X, yeah.
Okay, and then
And the
X, Y will be
Moved
raised
up
to
to 2, yeah.
Okay.
And if you kind of suspend your disbelief, you kind of sort of see it. But GeoGebra is definitely the way to go in terms of getting the truest sense. And if you want to kind of jazz it up here a little bit, you can, just do a little something like this. Give it a little flair.
Look pretty.
Yeah, you want to make it look a little nice. But let's GeoGebra. And a 3D graphing, and then we bring it up right there. So I could do the X equals, what was it? X equals 4 is what it was. And then Z equals 2. That looks exactly like what I created.
Couldn't tell the difference.
Yeah, it's like the spitting image. Now I just turned off I wrote them separately, but I turned them off. You can see how it's the same thing even if you write it in equation form.
What did that look like when you had equals 0 not in there?
Oh yeah, that was, let me just clear it out and rewrite it because, oh, there it is, yeah. It's a variable defined as a function of z in terms of z.
Huh.
Actually, sorry, a function of y in terms of z. So that's what this is really.
Will we be doing that this semester?
We will, yeah. This is, it's hyperbolic, right? That's because you could define one function as an inverse of another in any form. So if you look at this as y equals, you could define z as a ratio of x to y, or you could define x as a ratio of y to z. So in either way, you're creating an inverse relationship, and they end up having this hyperbolic look to them, and
I can't wait to
pretty
do your
cool.
hand drawing on that.
Oh, the hand drawing will be epic. Nah. No, what I do for these, actually, I should do a hand drawing. Attempt it. Nah, what I do is I provide you with a graph because those are just too crazy. All right, so in 2 space, what would the second one be the equation of? A circle. No, in 2 space it would be a circle, right? But it's going to be a cylinder because it is a cylinder for all z. All right, so what we're going to do is we're going to establish what we call a trace of the value. So we're really just going to focus on what it would look like on a single plane and then project it out in infinite z.
Is there a way to really define the set of points in one, or is it just all x, all y, all z? Yes.
In the first one?
No, so you know how in the first one we had the symbols and defined different points. So is there any way to do that with sphere and the traditional,
A sphere?
or a cylinder, for example, where it's defined as?
Oh yeah, z equals.
No,
Yeah, you'd have to, it would be a function of 2 variables. You'd have to write it as f of x comma y, but it would be 4 minus all of this equals z, and that allows you to vary, instead of just being 0 equals, it could be anything equals. So one trace of that would be cylindrical, but you're not limited to that. That's the thing, so it's kind of cool in that regard. In this case, what we want to do is just figure out what it would look like when z is equal to 0, which would put us on the xy plane, right? And so when you have a choice in the matter, that's really what you want to do, is just kind of work off of what you're familiar with, right? So we have a center of 2, 1, and a radius of 2. So I'm going to go out 2 units in the direction of x, and then 1 unit in the direction of y. So that's going to put me like right about roughly there. And in most cases, you're looking at just eyeballing it because, I mean, unless, well, let's just put it this way. If you're hell-bent on breaking out a ruler in order to make this precise, then I would have to grade you on your precision, which is just more work for everyone. So definitely not what I want to be doing, and neither do you. All right, so a radius of 2 will give me 2 units back in the direction I came, so that'll go 2 units that away. I can go 2 units that away. Say it again. All right, so we got our center of 2, 1. We're going out two units in any direction along the XY plane. All right, we'll go in the convenient directions and create a quote-unquote circle. All right, well, you could try to break out a compass for this, but since it's a perspective drawing, what you're going to draw to represent a circle is not going to be perfectly circular. It's going to look elliptical, but we're going to call it circular. Right? So this is the trace of the cylinder on the XY plane. So now what I want to do is just give it infinite height. All right, so I'm going to tack on all possible points in the z direction for each one of these points associated with my radius. So how do I do that? Well, I'm not going to create another circle up here, up here, up here. What I'm going to do is I'm going to draw lines. All right, I'm going to draw lines parallel to the z-axis going through those points. I'm going to try to draw lines parallel to the z-axis going through those points. And so I have that one, that one, and that one. All right. And then what I want to do, because I'm going to have to truncate this a little bit, I want to keep the same structure of the circle. Right? So this circular path should be replicated on the high end and also on the low end. Maybe you call this the lowest end of your graph. It's fine if you do that, as long as you create a cylinder out of this. All right? So what we would do, and this is where freehand becomes definitely the way to go, because if you don't do a freehand, you're at this for a while. I was gonna copy and paste my curves, and that would have just upset everyone. No, that one's gonna be too poor quality. Oh, I almost had it. That's the ticket. All right, so all you're doing is replicating your circle, as best you can. All I care about is the quality of your trace, your initial curve, projected out into the z direction.
The sphere?
The sphere is a different story altogether. What you have to do, let me just get this in here real quick. So some points here I got to get rid of. The sphere, you have to actually do a bunch of different traces. So you would figure out a circle with a radius of 0, which would be a point, then a circle with a radius of 1, and then a 2, and plot each of those. And then so you're actually building the shape of the circle. It's terrible. That's never anything I'd ask you to do on a test. That's why those kind of questions are reserved for tech assignments. tech assignments are the kind of things that people don't appreciate until you realize what they're saving you from having to do on other assessments. I'm just trying to get my points lined up somewhat reasonably. And there's a center there, point, point. And there's my cylinder. All right, so I'm just gonna pop a little star on the last one, and that'll be what you're going to do for homework, in addition to a bunch of other things I asked you to do for homework, and then that'll be the end of the store. All right. So 52, describe the set of points in three-dimensional space that satisfy this equation. All right, so what we have here is a center of 0, 1 with a radius of 3. The issue is it's not x, y like it would be, like it was in the previous function, like it would be in 2-space, all right, or the xy plane anyway. It's x followed by a z value, all right? So we're centering this right now, and then we're going to go out 3 units in the xz plane, all right? So we have to sort of visualize what the xz plane looks like. But again, we have kind of a glimpse of that, because here's x, here's z, it gives us our perspective. Going 3 units in the z direction, that's not going to be hard. Oh, I screwed it up immediately, which is what happens when I say something's not going to be hard. And then we have to go 3 units in the x direction. All right, so
You went 1 too many units in the...
I did it again?
Yeah.
Jump it, Jiminy.
There you go.
Look at that, I'm demonstrating I can possibly count. You know, if I study and practice enough, maybe it'll happen.
Maybe you get a degree in it, maybe teach one day.
All right, so I'm going to plot a point over here, roughly. Call that 3, because what I'm looking for is this is 3 units along the x-axis. I'm taking that, oh, I'm a little off. I can scooch it. I'm going to take that same distance out from x and plot a point, and then do the same distance in the opposite direction. And again, it's just a ballpark. And draw a circle through it, quote unquote circle. It's not going to be much of a circle. I mean, you know. Ugh.
It's 3-dimensional.
Yeah, just
Perspective.
yeah, suspend your disbelief. Yeah, I know. All right, so what we have to do is give it some thickness, and what this implies is that it exists for all values of y. So for all y, I'll just make a note. So I have to give it thickness in the y direction. All right, so what I'm going to do is I'm going to shoot out my points horizontally by an equivalent distance, however you want to go. Just keep that distance consistent. That might help you right. Oh wait, no, I think it's fine. Oh, because I'm plotting the center for some reason. Okay, that's what was messing me up. All right, so we're looking at a similar figure. And then if you feel like you haven't gotten the job done, maybe you do the same thing going in the opposite direction. I feel like I could probably give it a little bit more oomph. But it's really just eyeballing it. Let me go blue, actually, for these. I'll do it for the center also. I'll just plot that point so we have it.
That's wrong. Here's the timber that you had from
And a nice, smooth, crappy curve through it.
We got the idea.
And then there you go. Look at that beautiful cylinder.
better than mine.
I did a great job.
That looks really nice. No, right? Mine is the best.
I'm just going to trace over the outer boundaries, hoping to make it look less like crap. But I think I'm not succeeding.
I went to art school.
Yeah, I miss my calling, definitely. And then, like, blur your vision a lot so that all you see is the black curve. And then turn your head, and it's a can.
Art.
Yeah, oh yeah. Ay, ay, ay. Yeah, but obviously the bar is low.
Wait, so what if we're gonna have, we think maybe on a test we're gonna have an ellipse? That's.
No, it's got to be a cylinder. I can't draw anything else. Like, I wouldn't even be able to make the answer key. Like, I'd have to go to GeoGebra to do it. And again, like,
You get a zero.
yeah. I mean, there's some things where I'm like, all right, I don't want to do it, so I shouldn't have to make you do it, but I got to do it because it's a necessary part of the course. This is like, I mean, I don't even know if it's necessary to test you on it, but I figured it'd be a nice, easy way to get full credit for a problem and not have to go too crazy, you know, like it should be a mental break.
I used to do this really like lazy thing where my limit.
I feel like I was.
Yeah. But then you get to things like, I don't know, a limit comparison test for sequences and series and things like that. And you're like, it'd be really nice if I knew something about limits, because this makes a lot more sense if I know limit rules. This can be along those lines, but not so much, because it really isn't as algebraic as some other processes. What we're going to do is rely on what we know about three-dimensional space in order to help us find limits. Now, that being said, sometimes it's a plug and chug situation, in which case, you know, have at it. Limit rules, I mean, these are, believe it or not, these are Calc 1 limit rules just defined in terms of two variables rather than one variable. Right? So limit of the sums is equal to the sum of the limits. Limit of the product is equal to the product of the limits. Limit of the quotient is equal to the quotient of the limits. Right? So that works in 3 space also. You can add another dimension, it'll still work. Right? But in terms of just actually finding a limit, sometimes it's a matter of saying, all right, x is approaching 2, y is approaching 1. Plug in a 2 everywhere you see an x, plug in a 1 everywhere you see a y, and bon appetit.
Hardest mess yet.
Sure. I'll give you one like this. Actually, none of them are going to be overly complicated. The squeeze theorem ones will get a little tricky. I screwed up?
You screwed up.
Is 4 plus 6?
Too cute.
Which one?
2 times 2 squared. You wrote us.
Oh, I just lost a 2 for some reason. All right. That's why I need a TA.
I didn't do that either.
So they can screw it up and I can get on their case. Like, oh, clearly that's wrong. I was at a teacher conference, and it was about learning how to teach ENLs. So, what is it? English as a new language.
Yeah, no, it's
Y-
English. No, it's that.
They change the acronym like every day. It used to be that, then it became ELLL, and now it's ENL. And so, like, that's, what's that?
Was it one?
ENL now, apparently. English as a new language. So, like, I was learning some strategies, and I'm trying to incorporate them a little bit, you know, because I realize that, you know, sometimes the way I speak doesn't always make sense. You know, like if you're just learning the language, like, what the hell is this guy talking about? So I'm in this class, and I'm learning, you know, how to deliver content to people who may not understand me under normal circumstances. And there were some other math teachers there, and the person who was teaching the course is not in any way a math teacher, but she was trying to give an example, like she was just doing simple division. And she was trying to give an example of how, like, an ENL student would learn, and, you know, how I might, you know, like I would explain my thoughts, like what I'm thinking, and she would explain what an ENL person would be thinking. And one person raises his hand, and he's like, sorry, the answer is 108 3/5, not 108. And so I looked at him, I'm like, hey, I mean, somebody could completely miss the point of the entire, it was not about the math, it was about, like, dude, like, we're trying to learn how to explain a concept, not, like, it's technically not that. Like, yeah, okay, cool, you've mastered 4th grade math, cool, like, we're so proud of you, bud.
Yeah, no, teacher.
I wrote his name down, so if I ever cross paths again. Works out. So anyway, a limit problem here, you know, like in the case of the previous one, we'd like to have those all day, but this one says show that the limit does not exist, which can be infinitely more frustrating because you can kind of show that it might not exist, and you could come up with many circumstances in which it does exist, but where it does not exist, well, you could try to plug and chug. Just direct substitution. Replace your y with a 0. Replace your x with a 1, your y with a 0, and leave that -1 there. And you get 0 over 0, which, unfortunately, it means you got a limit. Right? It means the limit exists because if you think back to Calc 1,
Some of those rules.
it's telling us that the fraction can be simplified in such a way that a common factor can be canceled out. But you look at this and say, I don't know. All right? What was another strategy that you learned to handle indeterminate cases for limits?
Be like 0.9, 0.999.
Oh, a numerical way? Yeah, you could do that. But the problem with 3-space is you're not just coming from the left or the right anymore. Coming from every possible direction. So you could approach 0.999 from one side, from the other side, but you could be approaching infinity from the third side.
Like, get it in a way that you want it to look, and then just divide it by, or like undo it. That way.
Generally, sure.
I don't know if you could do it here, but like.
Well, I was looking for L'Hopital's rule. That's a possibility.
There it is.
The issue here is, I mean, can we take a derivative of something as a function of 2 variables? Well, yes and no. You can do it using implicit differentiation, but in 3-space derivatives work with partial derivatives, where we treat one variable as constant and differentiate in terms of the other one. So that opens up a different can of worms. All right, but the idea of holding one variable constant while you work with the other one, that could make sense. All right. So what you might consider doing is saying, all right, I only care about the path. Maybe you only care about the part of the graph that's in the xy plane. Right? Maybe you care about the path that's at the z = 2 level, right? Whatever it is. But somehow we got to get x and y to approach the point 1, 0. But again, we don't know where z is going, so it's not like I can say, well, let's let z = 22 because I don't know what z is supposed to be anyway. All right? But what we can do is assume that x is equal to 1. All right, and I'll give you a visual on that with GeoGebra, because I mean, you've seen the diagram. Like, if you want me to butcher that, I'm happy to.
Why are we assuming it's equal to 1? It already says it's equal to 1.
Well, it's approaching 1. I'm going to assume that it actually got there.
Oh, okay.
Why do you say in your notes that it's very hard to prove a limit exists?
What are you looking at?
Why do I say it's
So
very
I was
hard?
trying to skim it to see if we could get it on speed, and like you would just verbally said that it's very easy to prove a limit exists. And your notes were like, no,
It can be easy to prove. I don't know where I say what. I just copied this
First
from a
bullet point
textbook.
at, like, at the
The
end.
limits that exist to a functional solution.
Yeah, there's like words there. I never read them, so if they don't make sense, let me know.
Does not exist. Shouldn't it be the opposite?
Yeah, that's what I was thinking.
Yeah, it should be like it's easier to prove the limit exists and harder to show the limit does not
Substitute it
exist.
if it exists.
No, no, it's actually correct the way it says. Yeah.
Yeah, so it's easy to show it
Based
doesn't
on the
exist.
preamble here, for a limit to exist, a function must approach that limit for every possible path. Can you account for every possible path on a surface?
Only on one path.
Well, that's the thing. I'm going to make an assumption and create a path and go from there.
Oh, okay.
But if I don't have anything to assume, then we could be in a tricky situation, as you'll see in
Let's figure it out now.
4 minutes. We're going to assume x equals 1.
Oh, shit, screw it up.
Computer. All right. Shockingly, this graph is what the paper version was supposed to look like, even though it came from GeoGebra. I can't get it to rotate, so I just tried to pick a decent angle and plotted it.
Oh, that's not.
But this is what it looks like in space. Now, I popped in there x equals 2 to give you the part that I'm holding constant. All right. I can also plot. Well, actually, no, I can't because it doesn't exist. Or at least it doesn't exist based on this function. It just gives me a 0 over 0. But I can get a sense of where 1, 0 is.
Graph the function is wrong.
Sorry?
It's a minus.
Oh, it's -1 instead of
Ah.
+1. That's what I was looking at.
That changes everything.
Change it up a little bit.
Yeah.
Are you holding x equal to 1 constant?
I'm getting there. Yeah.
Slowly but surely.
So you just don't have an entire line through the
That's why I
function.
haven't gotten there yet. Sorry?
You don't have like that entire line where it's undefined. That's where it's rotating around. I guess the z-axis. Like it's just completely undefined at 1.
It looks like it could be non-existent completely, but there could be a point there. It's just too hard to tell because I zoom in and it doesn't seem to clarify anything. Maybe there's some actual points in that area, but maybe there isn't. It's too hard to tell. And then when I zoom in too much, then all hell breaks loose.
I'm gonna have to search this.
Oh, I zoomed out. Well, anyway,
Apparently lost it.
yeah,
There it is.
undo. All right, so 1, 0 for x and y. So I can pop that. I put in x equals 2 for some reason. Not corresponding with the way I want. All right. So what I'm looking at here is an intersection between the plane x equals 1 and the graph. All right. Depending on the angle, you get kind of more meaningful view of it. But you can see that there are plenty of graph that exists at that intersection. It's just a question of what's going on at 1, 0, 1, 0 something. So along this line. All right. That's where the interest is. All right. So it looks like there could be some z value that exists there. All right. I can also, the other possibility is that we could assume that z equals 0. Y equals 0. And then you have an intersection, and it kind of narrows things down a little bit so that you can see that it's living on a line in this area. It's just a question, again, of what z is going to be if you're on that line. All right? So, back to the math. Let's actually hold x as a constant and say that I only care about the points from this function on the x equals 1 plane. All right, so those are the only values that are relevant. I want to see if anything will exist. All right, so that would mean that I'm looking at the limit as only y approaches 0 of y over 1 plus y minus 1. All right, because I'm treating x as a constant, which you would naturally substitute in. And so the only thing that would involve a limiting factor would be the y variable, in which case I get the limit as y approaches 0 of y over y, which is 1, which makes it seem like the limit exists, which seems counterproductive. But again, what I need to do in order to show a limit exists, I would have to show that all paths lead to the same z. In order to show that it does not exist, I just have to show that any one path would lead to a different z. All right? So if I'm on the x equals 1 plane and looking at the intersection between that and the given function, what it's telling me is under those circumstances, the z value would be equal to 1, all right, as I approach the y value of 0. All right, so let's go the other way and assume that we're living in the y equals 0 plane, in which case I'd only be looking for the limit as x approaches 1, and that would replace all of my y's with zeros. Zero over 0, thank you. 0 over 0. All right. So then, you might look at it as a discrepancy. That could be an issue. I mean, if you look at this and say, oh, look, they're not equal, and I'm going to call it a day, that could be a problem because this is still 0 over 0. The 1 minus 1 cancels to a 0. You still have zeros everywhere else. So that's an assumption that it didn't really lead anywhere. And in fact, it would mean that you'd be able to simplify further. All right, but what you can do is you can maybe try a different path. All right, because when you're looking at a surface, there are, like I said, infinitely many paths that you can follow to get to a point. All right, as long as those paths exist on a real plane, then you really have no limit. And you'll see how that expands in a few minutes. All right. So maybe you try a case where you're coming in on the path where y is equal to x. I don't know why I stood up there. That was weird. All right. The idea is what I'm going to, based on the substitution of t, is I'm going to try to get this down into a single variable. Instead of being in terms of x's and y's, I'm just going to make it in terms of t. All right. So if I do this, I'm letting x equal t, and if that's the case, then y would be equal to t minus 1. So we're coming in on a different path, a linear path, but it allows us to streamline this down into a single limit, with the end goal being that I get something, because I'm trying to show a limit does not exist, I get a limit other than 1. Because this one, again, it didn't do me any good. All right? Although, I just want to see something real quick. If I did, I could show you a different way on the purple stuff in a second. So it would be the limit as t approaches 0. T approaches 1. All right, because this has to equate to equal these limiting constants. All right, so x needs to approach the 1, y needs to approach the 0. So that would work. Then y gets replaced with a t minus 1. X is t plus t minus 1 minus another one. t minus 1 over 2t minus 2. In which case you have a common factor of t minus 1. Simplifies down to 1/2. Right. So because that's not the same as 1, you're pretty good to go there. So I guess I don't know if it's worth talking about the purple again. Because the thing is, you can leave it in terms of one variable without doing a substitution. So I could have left the y's in there and simplified, and gone from there. I'm sorry, the x's in there and simplified, but the ship has kind of sailed. Anyway, so therefore, limit does not exist because not all paths lead to the same result. Result. All right, not all paths lead to the same result. All right. Yeah, it's kind of weird. I'll do it anyway, but I don't like it. I did all the substitutions in one shot, which really amounted to what we did in the setup for the purple. But the idea was that I knew where it was going to go, so I didn't think it was really necessary. But if you leave it in terms of x, so just only make your substitution for the y part of it. So let me get rid of that. You could say the limit as x approaches 1 of 0 over, leave the x alone, plus 0 minus 1. Is that right? Because the y is 0, right? Before you even get to the point where you would apply the limit, you would then get a simplified form of 0. And so the limit of the constant would be equal to the constant. I tend to steer away from that for a couple of reasons. The first reason is that, first off, I kind of forgot to do it, but this is the most commonly forgotten thing when people tackle a problem like this. They forget that they can actually simplify the fraction before applying the limit, which is kind of like, limits 101, I guess, because the limit of a quotient is equal to the quotient of the limits. So this is the same as saying the limit as x approaches 1 of 0 over that. And once you have 0 on the top, if this is a variable quantity and it could be anything, algebraically it would simplify down to 0. But it just doesn't feel right. And it feels like it should still be a 0 over 0 through direct substitution. So technically, every resource that I've ever investigated has said that this is the legal move. It gets it down to 0. I just don't like it. This method works all the time. It's just, you can see it's a lot more work, but it's a more satisfying answer because you chose a path. You have one obvious path. You chose another path. Those two paths did not give you the same result. In which case you can conclude definitively, well, the limit does not exist because these two numbers are not equal to one another. This one is that gray area where you're like, is that a legal move? Can I just take the 0 and divide it by x? Am I allowed to do that? Technically you are allowed to do it, it just doesn't feel right. Let me show another example because this is something that it's really important, but also, you definitely need some time to kind of get a handle on it. And also, number 2 is one of those kind of crazy problems where no matter what you try off the bat, nothing seems to work. You try direct substitution, you get 0 over 0. I don't think you need the work for that. Yeah. If you do, assume, I'm just going to stop trying to write in script. And I can't write in non-script either. How do you spell assume? 1 M or 2 M's?
1.
X equals 0. And then we'll do y equals 0. All right, so these are assumptions. If that's the case, I'm just going to do my direct substitution, replacing all x's with zeros, in which case I'd be looking for the limit as y approaches 0 of 0 times y, which is 0, over y squared. And the other one would be limit as x approaches 0 of 0 over x squared. All right, so we're popping in our constants and going from there. Now, that wishy-washy move on the previous page, if that's true, that would allow each of these to become 0. And it is true, so it does. It'll never feel right. All right, so you can make that, or you could do your direct substitution and get 0 over 0 again in both cases, in which case you're like, well, that did nothing. So either way, I'm trying to show a limit does not exist, and I just showed 2 cases where it might actually exist. So what I need is something that's going to allow me to show that it does not exist by giving me values that are different from 0. And if you don't even come up with these in the first place, what you need to do is choose 2 paths, 2 unique paths that could be on this surface that would give different limits. All right. The good news is this is a function that exists everywhere. All right. If you think about domain, that's why we're talking about domain. There's no restriction to x and y because on the top, you put in a real number for x and y, you're going to get a real number. On the bottom, sum of squares are always positive. You're never going to get 0. You're never going to get an undefined value. All right. So it doesn't matter where you are. You could pick any relation between x and y, and it's going to be fine. All right, so I'm going to go simple, or as simple as I can without using x equals 0, y equals 0. I'm going to try y equals x. Now, in this case, I can do that because x and y are both going to the same point. They're both going to 0. All right, so I can redefine my limit where x is equal to some variable t, and y is equal to some variable or parameter t, right? And that allows me to say that the limit as t approaches 0, right? Because both x and y are going to 0, and t is taking on the role of both x and y. And the reason why t is taking on x and y is because I'm relating x and y. If I call tx, and I'm also by definition going to be calling ty. All right. So if that's the case, then I'm looking at a new relation, t times t over t squared plus t squared, which would be the limit as t approaches 0 of t squared over 2t squared, which is the limit as t approaches 0 of 1/2, which would be 1/2. All right. Now this particular choice for a function, it only works because it allowed me to simplify my variables out of the top and bottom. All right, that's something to keep in mind. Because if these didn't cancel away, if the t squares didn't cancel away, then it would still go to 0 or 0 over 0, and it wouldn't further the plot at all. But once I got to a value that was other than 0, that's where I know I was good to go.
Could you just do like y equals x and just substitute in just x's wherever you see a y?
As a shortcut,
Like instead of going and defining everything in terms of t and then redefining based on that.
so it's a question of, is that sufficient to get the work done? Yes. Is it technically correct? No, because this path is the line y equals x as I would imagine it in 2 dimensions. But as you know, the line y equals x doesn't exist as a line in 3 space, right? So if I were to plot y equals x on GeoGebra, it's going to give me a plane. What I want is a single path along the curve corresponding with the intersection between y equals x and the curve itself. So technically speaking, we would have to parameterize this so that 3 space understands this linear function. If I don't do that, then it's technically not mathematically correct. However, I need you to show me that 2 limits are not equal to one another. Short of cheating, I honestly don't care how you do it. All right, so in this case, we're saying the limit does not exist. Not all paths lead to the same outcome.
Shorthand that to like 2 of your paths, like the 0 is not equal to 1/2.
Yeah, as long as you give me some explanation, just don't do limit does not exist.
Okay.
Because I mean, people do that all the time. I don't know what about this tells you that the limit does not exist other than show that the limit does not exist. So I'll just write some math and write limit does not exist. Nah, that's not gonna work. You gotta give me a little explanation.
What if the limit goes to infinity?
If it goes to the same kind of infinity, then the limit would still exist at infinity. But if it goes to different infinities, then that's fine. Now, if you got 0, 0, and infinity, good to go. Because that means that one side is asymptotic or one path is asymptotic.
Even if it went to infinity, then go is the L'Hopital rule, right?
If it's infinity over infinity.
Wait, when you say good to go, do you mean like it exists or it doesn't?
Good to go is in you've solved the problem correctly in that the limit does not exist. That's an example of what I was learning in that class.
So what's with the, sorry, this is just a notation thing. Why'd you write L in TNE?
Limit does not exist.
Oh, limit does not exist.
Yeah, it goes either way.
I just,
Yeah, so you're saying that the limit, earlier you said that the limit does exist, just they don't all go the same path.
There will be a limit depending on the path that you're following, but an overall limit for the function at that location would not exist.
Oh, okay.
Many people won't write the L in front of DNE just for technicality purposes, because I think I do it all the time in Calc 1, where I'll say what's f of 2, and there is no point at 2, so it would be no solution. Or you could write it does not exist, but the minute you put a little L in front of that and you write LDNE, you're not answering the question I asked you. If I say what's f of 2 and you say LDNE, I was like, yeah, cool, I know the limit doesn't exist, but what about f of 2? You know, so if you're ever in doubt, don't put that little L in front of the DNE, but technically it's correct to write it that way. That's just more of a student strategy. Now, this one, you know, we plug in the zeros, you get 0 over 0. Again, you don't need to work on that. You can probably bet that the same thing is going to happen if you follow different paths, but I'm going to do it anyway. So we're going to assume the path. I don't know why I keep doing that. Like, I haven't been required to write in script in like easily 35 years. But then for some reason I want to write that particular word in script. I don't know. Yeah. Yeah, I appreciate all those nice compliments. All right, so if we're assuming that the x value is going to be equal to 0, then we're going to get x over y to the, 0 over y to the 4th, particularly as y is approaching 0, because we're on the x equals 0 plane. And we're only following the path on the curve intersecting with the x equals 0 plane, moving closer and closer to y equals 0. In theory, from 2 directions, because we're cutting it on a particular plane. So we have a path now. Instead of that open field, and you can be coming from any direction, you're coming from 2 directions. So if the limit is the same from the left and the right, you're in good shape. All right. So in this case, though, we could simplify. This becomes 0. And so the limit of 0 is equal to 0. All right. So then, and you know, you could graph some of these functions and get a sense of it in 2 dimensions. Just when you have 0 on the top, it's definitely more challenging. But let's say, for example, if we have the path of x equals 1, I plug in a 1 for this, and all the x's go to 1. Now you're looking at a function of 1 variable. That's something you can put in your graphing calculator and actually look at, right? Because you're actually bringing something down from 3 space into 2 space, all right? So do the same thing for the y's. So for y equals 0, you're going to get x approaches 0, and we're replacing all the y's with 0, so 0 over x squared. We're looking at the limit, because again, this mathematically computes to equal 0. I did a y for some reason, which gives a result of 0, so no help there. We'll get it on the river. So now I need a third path. Any path that's going to distinguish a limit or create a limit that distinguishes itself from these two. Well, one of these unique limits. All right. So the issue is you might try what we just tried. You know, if it ain't broke, don't fix it. So try y equals x. The y equals x path, which corresponds to x equals t and y equals t. Both go into 0, so it's a legal move. Now again, keep an eye on what your limiting constants are. Because if this is like 2, 0, then you'd be looking at an x value that's 2 more than your y value. Right? So you'd have to create a relation that works off of that. All right? But it's going through 0, 0. If this were in the xy plane, the line y equals x does go through 0, 0. So that path should lead us to where we want to go. So I'm looking at the limit as t approaches 0. This would become t cubed over t squared plus t to the 4th. That's not going to do it for us. I mean, you could try to factor and simplify. I suppose you can get somewhere with that. Maybe it does. Maybe I'm just misremembering. I'll try it. Got a common t squared. Pull it out and kill it. Sounds final. T over 1 plus t squared. In which case you get 0 over 1. The better answer, I guess, but unfortunately not a unique answer. Like, dang, I'm going to be at this one all day. Right? But what you have to take into account is that you could choose any function you want that relates x and y. Anything. All right? Because this is a real function. Right? There is no restriction to it. X exists for all real numbers, y exists for all real numbers, which means that there are infinite relationships between x and y. So if I want to say y is equal to the sine of x, I can. I don't know if it's a smart idea, but I can do it. All right? If I did do that, then I'd be creating a trig ratio out of this, a ratio of trig ratios. That sounds gross. Bless you. So start small and think bigger. A little strategy that you might want to employ would be to create a relationship that allows you to have common powers in the denominator. All right. That took off on me. So if I say, for example, that y is equal to x squared. Oh, x is y squared? Yeah, that'll do it, right? Because if x is y squared, that'll make them both y to the 4th. At least I can combine them. All right, that's a thought. If that doesn't work, then we're grasping. But what I would say is start with the simpler parent functions and then work your way out from there. I mean, there's no reason to think that you'd have to start with an inverse tangent function as your relationship between x and y. Start with something simple and then work your way out from there. All right, if constants aren't getting the job done, then go further. All right, so x we'll define as t. All right, y squared is equal to x. All right, so if I replace an x, well, maybe I want to go the other way. Maybe I'll let y equal t. Just to keep it, to avoid radicals. So y equals t, in which case x would be equal to t squared. All right. Otherwise, I'd have the square root of t in for y. That's not as appealing. It would still do the job exactly the same way, just not as nice. So limit as t approaches 0, t squared times t squared over t to the 4th plus t to the 4th. Limit as t approaches 0 of t to the 4th over 2t to the 4th. And I think you're getting the moral of the story here. If you have to take a guess on what the unequal limit is going to be, take a shot in the dark, it's probably going to be 1/2, because that seems to be what's happening here. No, it's not always going to be that way, but the examples I chose, it did play out that way. All right, but again, the minute you show a limit that's unequal to the ones that you came up with previously, you've done your job. The problem is it could take 10 or 12 attempts in order for you to get there. So limit does not exist.
Are there any values in which a limit does exist? Or any equations, I mean any equations.
Oh yeah, we're going to get to those next class. The squeeze theorem is really the avenue for that. Oh, it's much easier this time around. Because I'm teaching it.
I've gotten like very much breathed by. I really don't remember learning that.
Yeah, I'm gonna treat it as though you haven't seen it before, because I remember a lot of hand waving when I was being taught that, where it was like, all right, so if you have a function and it's got a limit, and you got another function and it's got a limit, and there's like one in the middle, if those two functions have the same limit, it would have to sandwich or squeeze the middle function in order to have the same limit. All right, moving on to derivatives, and that was the extent of the lesson. So, yeah, so that's probably what you got. Yeah.
Makes sense though.
Oh yeah. Oh, I understood the concept fully